over to Guido Herrman from the University of Manchester. Guido, if you'd like to share your screen.
Yeah, is that visible already?
Yeah, that's great.
Okay, good, brilliant. Thank you very much. Good morning. Thank you for having us here today. Our intention is to speak today actually about human-robot interaction, and this is a follow-up pretty much to the activity in the early part of May, on the 7th of May, and this is being organized through John Dukes, who is our RAIN program manager, and myself. I'm from the University of Manchester. In terms actually of what we're going to do today, I will introduce the idea why we're doing this at first. So what is HRI? Why are we having this set actually of webinars here? And then I will also introduce a plan we have in terms actually of a workshop, of a HRI workshop, particularly also including actually industry and jointly organized with the Knowledge Transfer Network. After that, we will have Emily Collins, Ozan, and Erwin talking on their topics. Emily more on human factors, Ozan on teleoperated gloveboxes, and Erwin on the estimation of human behavior in human-robot interaction. So from that point of view, actually, HRI is a fairly young research area. The first conference on human-robot interaction took place in 2006. And so I was contacted somewhere in 2007 by a colleague of mine to organize actually the International Journal of Social Robotics, which was founded in 2009. So the first journal actually in the area of human-robot interaction was founded in 2009. So we can see actually the whole area of human-robot interaction evolved over the last actually 12, 14 years, if you wish so. Human-robot interaction is about the science of safe and meaningful interaction of human and robots, where we have robots of various actually levels of autonomy. And we need to appreciate that this is actually some form of physical and social interaction. As we can see here, the lady there actually interacting with a now robot, but we also know about actually more physical interaction, such as the collaborative actually cutting actually with a cooker arm, or actually more social interaction here from this lab in Norway, but also actually early physical interaction examples such as this one. And we argue that human-robot interaction is also essential actually to teleoperation, telerobotics. We need to answer within the area actually of human-robot interaction various problems, various questions. It's about actually embodiment of actually the robot itself. Actually, how do we shape the robot? How do we actually set up the robot actually so that we feel physically safe, for instance, psychologically safe? Physically safe, certainly actually we need to have for that some form of maybe active or passive actually kind of control techniques which allow us actually that kind of safety. Communication with robots is important. So, and we are usually inspired here by human actually communication, language, gestures, and also gaze, touch. And that sparked obviously the kind of research actually which is ongoing in the area of haptics, virtual reality, augmented reality. So these are the research areas which actually come out of that kind of communication kind of idea. Certainly, actually, what is also important is actually cognition and perception. How actually is obviously the human action actually, recognized and predicted, and how do we act on it? And that actually sparks the second step, actually, how do we decide, act, and control the robot in such actually kind of domain where actually the human is physically part of that actually robot working domain. in that sense also sensing and actuation comes in. And so as we see, actually human factors is a core part actually of trying to answer various of these aspects where actually scientists, robotic scientists from computer science, robotics, psychology, and so on are working together. So from that point of view, you can see that we had actually already a webinar in early May. Chandra Varish, our theme lead, and his team actually at Sheffield actually were holding various talks on perception, communication and decision. And we would like to continue this kind actually of set of webinars where we will talk about actually human factors today and trustworthiness, sensing, actuation, communication, which is pretty much our practical actually considerations, practical setups at teleoperation. Again, perception and cognition, where we would like to understand what the human is going to do. We would like to estimate actions and predict these actions. We will have another third actually webinar on the 18th of June, and that will effectively be held by William Harvey and Peter Scarf on communication perception, also Ingmar Young and on a similar topic, but then actually William more on haptics and Ingmar on virtual reality. What is important that we are engaging actually with all the different hubs, and in particular we have also invited our colleague actually from the Bristol Robotics Lab, Alex Smith, who is from the team of Manuel Giuliani, Paul Bremner, Alex Smith. So these are the team members actually working pretty much on various aspects of HRI for nuclear. And they will be talking about decision and control, variable autonomy. I would like to summarize then on the next actually webinar pretty much the kind of activities we have across actually our two actually hubs, and then we would come to actually our idea of a UK-wide actually workshop on HRI with involvement of industry. Originally, also we actually have been planning actually to have a demonstrator, and hopefully this will come obviously a bit later in time. The demonstrator where we combine our HRI activities within RAIN, and we can show off obviously our activities. But what is important now actually that we take obviously the opportunity here in terms actually of obviously COVID, and push forward actually that workshop. The idea of the workshop is that it will be sometime in August, late in August. Evidently, actually, with our current situation, it will be web-based. It will be 2 days. And we would like to involve industry and academia, and certainly also UK research funders. We're coming towards the end actually of our hub on extreme actually conditions and robotics. So we would like to involve UK research funders, industry, and to look into the future. Hence the first day actually of that workshop will be more having an industry focus. In particular, the morning we will actually engage with, we would like to engage with industry, and we would like to ask industry, what obviously are your future views on HRI? And we would like to have this happening actually in terms of targeted talks, question and answer panels. Having that kind of idea, afterwards, we would like to return to the university focus and speak then about our actually progress in terms of various topics such as virtual reality, teleoperation, haptics, shared control, human-robot interaction, communication, human factors, and trustworthiness. And that would stretch over actually the afternoon on the first day, on the second day in the morning, to close up things actually on the second day in a obviously common discussion panel, and to understand actually where we go with this. So from that point of view, actually, the wider objectives of this actually workshop is to create a roadmap for HRI and robotics in extreme conditions jointly with industry, to share our progress and plans and effectively to engage also with funders for good reasons. From that point of view, actually, what we really want to have is the feedback actually from the audience here, where we are aware that some of you are from industry, some of you actually are also from funding organizations, and we would like to gain that form of feedback actually towards John Jukes. He is our RAIN manager, and as you notice, we are engaging obviously across actually the different actually hubs through actually that workshop. So this was pretty much the introduction. I would like to hand over to Emily. If you have any questions towards that introduction, please put them possibly into your chat. I will answer them through the chat. But I can hand over now to Emily, who will have obviously a more scientific actually talk now on human factors.
Are you okay, Emily?
Yeah, it's just sharing it whilst also being in it.
Okay.
Can you share it for me, please? Oh, wait a minute, where's it gone? Oh, there we go. Has that worked?
Yeah, that's great.
Cool. Morning, everyone. Thank you for joining us today. I'm going to be talking about challenges in hazardous environments with a focus on the human part of a human-robot interaction system. So when designing human-robot interactive solutions to working in hazardous environments, I consider context as essential prior to the design of whatever it is that you're going to be dealing with. There's a fundamental need to understand why things need to be a certain way, which changes how you approach the problem. In particular, trusting that your interactions with X will always result in a specific outcome is essential. But what does that practically look like? So in this talk this morning, I'm just going to be discussing some key issues that surround this situation. So I consider robots to be tools, although that's a potentially fairly controversial topic depending on who it is that you're dealing with. But let's imagine a human being using a hammer to hammer a nail into a wall. If I am the person controlling that hammer fully, I can guarantee every time, as long as I know how to use a hammer, that hammer will effectively hammer that nail into the wall. And if it doesn't, it's probably because I have a problem with my hand or the hammer is faulty, it breaks. A robot is a bit like a fancy hammer. So it's a hammer with more and more layers of autonomy in it, all the way through to full autonomy to some level whereby me and the hammer are working together in order to put that nail into the wall. So as that hammer becomes more able to do things without the need for my hand controlling it, you need to consider what the human is thinking to ensure that it trusts its fancy hammer to reliably carry on putting that nail into the wall. So that's just a thing that I think generally before I approach most human-robot interaction tasks. And just I'd share it with you. But to go back to context then, I'm going to use one example today of an industrial challenge to throw up all these questions of key issues, and that's fusion maintenance. But what I'm going to discuss is relevant across all sectors, anywhere that's affected by this fundamental issue of working in an environment that a human being cannot enter without great cost or risk. And a nice question to start with then is, other than whether or not the kit fundamentally works, what needs to be considered if you want to have an effective remote control slave device in an environment you cannot enter? I shall be providing no answers. So this is pretty much a talk about questions and key issues that come up time and again I mean, Ozan and Erwin later on will be discussing some useful methods, and check out Liverpool's work on verifications for your essential fancy hammer testing solutions. But this is more of a starting point to think about questions in human-robot interaction that are aside from, does the robot work? Yeah. So, fusion reactors. Your typical hazards in a fusion reactor, which make it a live reactor impossible for humans to enter, include things like the beryllium dust from the plasma-facing components, and the fact that it is, of course, radioactive. Now, it's a short-lived radioactivity, decaying in a mere 50 to 110 years, that still means that stuff that happens inside that live device is contained within that live device for its life. Our existing experimental structures are pretty small, and in order to make fusion a viable energy source, these structures need to get massive, like much bigger. And with their increase in size comes an increase in the complexity of those structures, which means prior to them being built, you need to think about all the mitigating circumstances which might result in the failure of the entire structure due to lack of access to maintain any part of that structure. And that means thinking about all the different questions other than, does my robot work? So the H in HRI, our user. There is no option for failure when devices or scenarios which a human cannot enter occur. Wait, that's a sentence, yeah. So your first question is, if there's no option for failure and there's a human being still in the loop in my human-robot interaction system, how does the no option for failure aspect affect the cognition and psychology of the operator, of that human that's still involved? Thinking about that allows you to start questioning all the different mitigating circumstances that go above and beyond just the robot failing. So a robot failing is dependent upon how it's being used, which means you need to consider all aspects of the context in which it's being used. What are the real risks? And if we go back to our fancy hammer, with layers of autonomy involved, who is going to be accountable at every stage of that interaction? So at some point in my fancy hammer use, it's going to do something that may or may not be my fault. And at that stage, who am I blaming? Who takes the fall for the whatever mishap my fancy hammer results in? Trust in my system is heavily dependent on who is responsible when failures occur and what the consequences of being responsible for failure will be. Now, this is a very great example of why I can't provide any answers right now, because what we're talking about here is mitigating for law and ethics 10, 20 years down the line for things that we're building today to put into scenarios which maybe don't even exist yet. Big questions. So let's raise some challenges then. Training. It is difficult to model, train, and plan for the interaction due to dynamic, complex, and uncertain environmental factors. Those mock-ups that exist of ever-increasing fusion reactors contain very, very complex plans with very small areas which, once built, will never have human beings inside them again. How do you pre-plan for all the sorts of things that might happen once they've been built? Now, mock-ups exist, and training on reactor mock-ups is essential, but mock-ups are very different to working with live environments. In a mock-up, if you drop something with your slave device at the other end that you're operating outside of the mock-up, you can go in and pick it up. But in a live reactor, you need to wait for that minimal radioactive decay time of 50 to 110 years before you can retrieve something that is stuck. And if that happens in a critical part of a huge fusion reactor worth, X number of monies, does the whole thing shut down? Do all of your investors lose their money? Who is responsible for that? There is no option for failure in live machines. So we'll go back to our H. Now you can probably understand that massive psychological shift that is required for an operator working between a training in a mock-up and a training in a live device. So how do you support operators during their training to prepare them for that level of intensity? And this goes back to our risk and accountability measures. If my kit works and my kit works fine, but then my kit is going into a place that I will not be able to go with it, what other things do I need to think about to make sure that the human that's still maintained in that loop, if indeed you still want a human maintained in your loop, I'm going to encounter? So we'll raise some human factor concerns. How long are shifts? Now, typical shifts on Fusion mockups are about 8 hours. And so you need to start thinking about all those sorts of feedback, sensory inputs that are coming back to you from your slave device at the other end, and how they're being received by an operator, which allow for continuous use over an 8-hour period. There's a lot of headsets, VR units, which are not optimal for such long periods of time in use. You need to think about things like maintenance of one-to-one kinematics, reducing cognitive burden on operators, because they don't have to think about where the slave machine is in relation to themselves. You need to accommodate movement of the human being, who can go backwards and forwards during their shift to avoid muscle stiffness, fatigue. You know, you don't want to wait for the toilet for 8 hours. You want to leave your machine and come back to it without having to then think about where it is in the environment that the other end is situated. And you need to think about sensory replacements. If you are physically used to maintaining a machine and you know that audio feedback from torque wrenching will allow you to know when to stop, and you now no longer have any audio input, what are you compensating that sensory feedback with? What do you replace those sensory feedbacks with? And then you have the pre-planning. So retrofitting will not work, and small things impact entire systems. So let's think about tool functionality. Inside a fusion reactor, your slave device will be working in, any which way, and knowing the angle that your tool is at by maybe only having a very minimal visual input is really important. So thinking about things like having spirit levels on unique tools so that you know exactly what angle it is at is kind of essential. And all of these sort of small things need to be conveyed to designers and makers before things like tools are commissioned. Even stuff like control room layout is vitally important. Where are your air conditioning units placed in a room? Are they strangely going to be positioned right above the necks and heads of people sat in VR units for 8 hours a day, giving them cold backs all day? And these seem like really small, minimal things, but considering the complexity and vastness of some of these industrial settings where you require maintenance but cannot have human beings, the builds of these structures are often very difficult to change after the fact. And vitally, throughout all of this, you are training a workforce to such a high degree that you kind of want to keep them happy, you want to maintain them. So when thinking about a human-robot interaction system, considering the human aspect, that H, and looking at that human being as, and I don't mean this in a bad way, but as much as a machine as the robot part, with all of their different biological systems that require attending to in the same way as the kit needs attending to, and making sure that those two things work together optimally and reliably, is how you produce an interaction that is worthwhile, not just today, but in 5, 10, 20 years. So my final thought is, it is essential to recognize recovery and failure modes and to mitigate all of them before anything is built, which is a big statement, but yeah, should leave it there. Thank you very much.
Thanks, Emily. That was really interesting. If anyone has any questions, please can you type them in the chat function. We don't have any at the moment, but we'll give it a minute or two just to see if anyone has any. Though I'm a bit conscious of time, so we can go on to the next talk. Just to, while we're waiting to see if we've got any questions, just to let people know that we don't have a session next week. Having a little break, and know that the ICRA conference is going ahead online, so I think lots of people will be going to some of their sessions. but we are back on the 11th of June. Still no questions. I think maybe then if we start with our next talk, and if anyone does have any questions for Emily, you can put them in the chat and she'll be able to answer them. So Ozan, do you want to start sharing your screen if Emily can take them?
Yes. Can you see my screen?
Yeah, do you want to make it full screen? It's just in...
Sure. All right. Hello, everyone. My name is Ozan Tokatli. I'm from RACE, working as a research engineer, and I would like to introduce you the teleoperated glovebox we're building in our company. So although Guido and Emily gave really nice introduction and brief information about what human-robot interaction is, I would like to mention that this is the field of robotics which studies the interaction between human and robot, and also the collaboration between human and robot. We can roughly group the field in two different interaction modes. One is the proximate one. A good example is haptic applications, where you use the haptic device to manipulate a virtual environment. And the other one, which is I think more interesting for us and for RACE, is remote interactions, where human and the robot are not at the same location, or they don't have a direct communication, physical communication. One good example is the jet remote operations with mascot. HRI is a vast field, robotics field. There are many aspects, and my focus here, especially my research focus, is on the physical human-robot interaction. So let's keep in mind that the human and robot are doing a physical interaction here. When Guido was introducing HRI, he said this is a new robotics discipline, and I totally agree with him. As a robotics discipline, HRI is a young subject. However, if we check the history of robotics, we can see some early examples of a human operator manipulating a hazardous environment or a nuclear substance using a robot or a mechanism. This was also a human-robot interaction example, but at the time it wasn't considered as we do right now in this field. But again, this is in terms of a discipline, this is something very new to us. So my aim today is to introduce you the teleoperated glovebox we're building, but I would like to build a background first, and then I will continue with the glovebox later. And to build the background, I would like to give two examples of my previous research and the things I learned from them, which will be useful to understand certain aspects of the teleoperation system we're building. The first one is a human-robot collaboration project, and the second one is a haptics project, which is used inside classrooms. All right, this is my first application example. A human and robot are collaborating to compress a spring. The task itself is very simple, and in fact it is designed to be simple, but in reality it is trying to capture a needle insertion example. Needle insertion is quite complex, a very nonlinear example, but here we build a very simplified and linear version of it. The aim is to compress a spring with a certain velocity up to a certain point. So as a research problem, we would like to design an interaction controller so that we can safely compress the spring, and also we have some high performance. So first of all, what I mean by the interaction controller, it is the regulator that controls the forces or the interaction between the robot and the environment, and between the human and the robot in this case. Safety is the primary objective for almost all physical human-robot interaction examples. We characterize the safety using stability of the closed-loop system, Performance can be measured with different aspects, but for our case, the performance is the transparency, the ability to reflect the environment to the human, or the amount of distortion created by the presence of the robot. Well, in this research, we selected a control algorithm, a control layout for our system. We identified the closed-loop transfer function. We identified the impedance displayed to the human. These are characterizing the stability and the transparency of the system. We performed a brute force search on a predefined domain, which is the domain of the controller parameters. We identified the stable controller parameter pairs, and then we continued the analysis with the transparency on the stable ones, and we observed there is a transparency stability trade-off between them. So when you have a good transparency, you sacrifice the stability. So this was a very, very brief introduction of this study. But what I learned is that designing an interaction controller is a very cumbersome process, and it requires the knowledge of robot environment and human models, which is quite tricky to obtain, and they're usually nonlinear and hard to work with. So, second example, using haptics in classroom environment for enhancing the learning. Well, haptics, very briefly, is the technology that enables you to physically interact with virtual environments. It's being used for simulators especially, but it hasn't been used or explored whether it's useful for classroom and teaching. On the other hand, biology is one of the subjects that students have hard time to grasp, especially they develop misconceptions because things they encounter are maybe not intuitive for our daily life. So we thought that we can use virtual reality, haptics, and virtual environments to build a better understanding for the student. We picked a multi-finger haptic interface to interact with the virtual environment. So there are two robots, one robot for the index finger, one robot for the thumb. So you can do a pinching motion, the robot will follow your two fingers. The other thing we use is a head-mounted display, which improves the immersive experience and gives you a stereo vision of the environment. We built a virtual environment which depicts a cell membrane. It's a semi-selective permeable membrane. Certain molecules can go in freely. Certain molecules need to go through certain ports. And we prepared them a worksheet like they do in their regular laboratory classes. And then we asked them to complete the worksheet in a certain amount of time. We conducted the study with 60 students, and half of these students performed the tasks with force feedback enabled, and some of them completed the task without receiving any force feedback from the virtual environment, meaning that they didn't feel the forces occurring in the virtual environment. So what we observed at the end is that, at least for the learning, the force feedback is not essential. But what we also observed is that using an intuitive interface for manipulation in the virtual environment is very crucial. Now, with these lessons learned, by keeping them in our heads, I would like to continue with our main topic, nuclear glove boxes. So these are very challenging environments. These are used to manipulate or manipulate nuclear and dangerous hazardous objects. There are certain risk factors here that you can encounter with sharp edges, which can puncture the gloves you're wearing, and therefore you have the risk of being exposed to radioactivity. The working conditions are really not optimal. You can't work for long hours, not just because of the radiation risk, but also the glove box and the protective equipment are not enabling you to work for long hours. So our solution is to replace a human operator from the glove box and put a robot in there, so that the same tasks can be done with using a robot in a teleoperation setup. So The master device, this will be a teleoperation system. There will be two parts, master system and the slave system. And for the master one, we picked to use the HTC Vive controllers because these are very intuitive controllers for tracking the hand motion. It's not like using a stylus or any other tool. It's just moving your arms, your hands, and we will obtain the motion information that we can use later for the teleoperation system. For the slave robot, we have a geometric constraint, and it is the size of the port. It's usually 6-inch, and the robot should be able to fit into that 6-inch porthole, and therefore we picked a off-the-shelf robotic manipulator for it. Another good thing about this robot is that the position and velocity controllers are already implemented, and moreover, the robot is capable of estimating the end effector force, and therefore it is capable of controlling the force at the end effector. So, this in the teleoperation scheme, what we have is a master device that tracks the human hand motion, sends the motion reference to the slave, and slave follows the motion reference using its onboard controllers. But it's not enough. I mean, in order to provide more sensory feedback to the user, we equip the glovebox with RGBD cameras, and moreover, we have a digital twin model, virtual twin model of the system. We built a mock-up glovebox. It has 2 robotic arms. It is controlled by the HTC Vive. We're still improving the control interface, but the system is capable of manipulating objects inside the glovebox. And also, we build the digital twin of the system. This is especially useful for planning and execution phases. It helps the operators to identify any risks that can occur during certain task execution. And so we instead of exchanging the force information, which can cause some problems in the control loop, we are just sending the motion reference, and we let the slave robot to handle the interactions with the physical environment and do the control on board. But on the other hand, the intuitive controllers that we use it reduces the task load on the operator and lets them use more, let them focus more on the task execution. Right now, our gloveboxes are not autonomous, and I don't believe that it is realistic to say that they will be autonomous in the near future. But what we are trying to do is we are trying to support, assist the operator during task executions. So in order to assist the operator, we are developing shared control algorithms based on the motion signal we are sending as a reference. This is basically exchanging this is basically scaling the motion generated by the operator depending on the certain environmental conditions and risk conditions. And moreover, we are creating optimal trajectory deformations such that the operator can deform the predefined trajectory for the robot optimally while the robot is moving inside the glovebox. This is especially useful if the operator identifies a risk that isn't being captured by the motion generation algorithm. HRI is not the only aspect in this research. I'll just briefly give some headlines from other research aspects we're doing. Optimal grasping is another research question that my colleague is working on, and he's also closely working with another colleague on the grasp detection and deep learning. Trajectory generation is quite crucial for our glovebox setup, so we are working on trajectory generation with physical limits, and automated maintenance of the robot is the 4th research aspect we are interested in. So this is basically my end of my presentation. Thank you for spending your time for me. And I'd like to answer your questions if you have any.
Great, thank you. Again, if anyone has any questions, please could you put these in the chat. We have had a question in there for Emily, so I don't know if Emily's on it and answering it. It's quite a long one, so I'll leave that on the chat for the moment. And again, we'll just give it a minute and see if anyone has. Oh, here we are. Got a question. Is the digital twin available for others to use?
Yes. It's not being actively used in the control loop, but it is available to the operator.
Okay, great.
I can answer the questions in the chat. I mean,
yes.
It's okay.
Well, following on for that last question, is it available to other research groups?
Oh, sorry. Yes, we can share them. We can happily share the digital twin.
So people just get in touch with you, or
yes, please. I will help. I will direct them to the right person, and I'll help them to get it.
Okay, great. Okay. All right. Well, if there aren't any other questions, just wary of time. So we've got questions. We'll have time for some more questions at the end if we need them. Yeah. So Erwin, if you want to start sharing.
Thank you very much.
Give me a second. I'll just come here and okay, my presentation. Good morning, everyone. Can you see my screen?
Yeah, again, can you make it? Yeah, that's it. Brilliant.
Yeah, lovely. Thank you. So, good morning, everyone. Thank you for the invitation. My name is Erwin Lopez. I'm a PDRA working at the University of Manchester. I'll be talking about some of the work done through my PhD that is relevant for HRI, or some of our ideas that we're thinking about applying for several aspects in industry and especially nuclear. So the long title, I will try to make it swift and entertaining, or at least informative. So a little bit of a table of content. I will talk about the background ideas that came about before our work, why are we doing what we did, and then complementing what Emily, Guido, and Ozan talked about human-robot interaction. I will introduce topics about modeling this type of interaction, the H with the R, let's call it, and two of these aspects that I will call task level and cognitive level modeling, with some more applications in hand. So to start very briefly, this is me, Erwin. I'm a mechatronics engineer from Colombia. I started working in very integrative projects in robotics, simulation, haptics, and simulator development for driving simulators, also diesel servoing. So my background was basically integrative work and technology, let's call it. And two of my collaborators, my previous supervisors, Guido Herrman and Untitled, each had a different strength of specialties. Guido Herrman, as you know, advanced control and robot control as one. But my other supervisor, behavior and perception, basically how humans understand and act throughout the world. And then these two combines goes to a work in HRI and social robotics, trying to combine all these two aspects, the control, but also understanding the human, and how we can do this through basically sensing and modeling. So again, as the two previous talks had, just a small brief through of what we consider human-robot interaction, especially including the environment, or what we could say the space or where the interaction happens. So if we consider human and robot with a continuous interaction, there's always an environment which the human interacts with and the robot interacts with as well, which combines them both. So they are interacting in a potentially open environment, which is a challenge from the robot perspective alone. We humans are designed to do this, so it's completely fine. However, dealing with human interaction from the robot standing point and the environment at the same time is quite challenging. Hence, we can understand better what the human wants to do, is trying to do, or wants us to do. Let's call it us the robot. As the interaction occurs, it helps us to have a safer and successful interaction for any other task that we want. In this context, my role and my objective is to understand the human as it is interacting with the robot. I put robot vehicle here, but it could be any type of autonomous or semi-autonomous being. I want to understand what's happening here in this interaction. If we can estimate or understand the human and the task being performed better, in a way that we get information about what the human is thinking, or let's call it the inner state or internal model of the human. And this allows us to better control the robot and make this interaction safer. That's basically the idea behind these concepts. And some of the tools that we use are in these three big pillars. I'm going to go very briefly about them. Considering human-robot interaction as a modeling based on the human, and understanding any old task and interaction based on what the human wants and when the human needs. Either we have a very autonomous robot or not. Understanding the human by means of models, of course, but also getting models on the go and information using physiological sensors. These understood as sensors that get the information about what the human is doing. So it could be heart rate sensor, eye gaze sensors, any type of sensor that gives us information about what the human is or wants to do. And we also focus on data-driven models, machine learning models, statistics regressions that, together with these sensors, can give us information about the part of the human-robot interaction. This, again, very briefly, I'm trying to be swift. But these ideas that we bring about are aimed towards this, understanding the behavior and trying to know what's happening now and what is gonna happen again later with the human, hence predicting any type of human behavior. How do we do this? We introduce two concepts basically. One about task level modeling that, as Emily says, it depends on the context. Any other tasks are different. Depending on the task that the human is doing, we can understand it with far more time ahead in advance and with different types of sensors. In our work, we use skeletal tracking, hence limb positions of the human, to understand what the human is doing. So this is an understanding of the human based on what a decision that he already made. And cognitive level modeling is information that gives us ideas about what is about to happen or what decision-making processes are happening whilst the human is doing them. So it could be the case that the human is performing a task, and due to any another scenario change in his perception or whatever, the human can change task, or either willing or unwillingly. This type of measurements are way trickier in our research. We use physiological measurements as heart rate, which gives us a physiological response to feelings, and eye gaze, which gives us information about attention, to understand if the human is about to, for instance, change decision, or a sentiment, feeling, or stressful situation is occurring. And this also, in a temporal framework, we describe it as having at least three steps. One is self-analysis, that we understand the underlying processes, followed with understanding what is happening now, of a classification, and a prediction, which we try to estimate something that's about to happen. In the task level, it's easy to do that. We think about reaching for an object. We understand how reaching works. We understand then now what object I'm reaching, but then the prediction can tell us where am I reaching at, what am I going to reach for an object or so. Very briefly again, this is part of our work that we did based on driving simulators. So the task level modeling, we took movement as the basis for understanding the task. We model the task using arm motion from skeletal tracking systems. Considering that human motion and human arm motion is highly variable, even between people and for people itself, for one person alone, all arm movements are different. However, for taught task, as driving is, hence we have a course where people tell us and teach us how to drive. This type of task have a repeatability, luckily, and we can tackle those patterns and model the whole situation. What I mean by that is something like this. That's a little bit modeling this being someone holding steering wheel. Oh, sorry, holding the steering wheel. We can understand the angles for the arms, the limb position, and try to model this for maneuvers in a driving simulator. Again, this is an engineering process where we set parts of the tracking, the tracked limb positions, and convert it to a task model, which gives us an understanding of the task at hand, which is driving. I know that we are a bit short on time, so I'm going to skip this lovely video. But then, for more interesting for the cognition level, we did something similar, but getting other type of sensory input and to understand something cognitive load. So what is this about? So if we consider cognitive load, at least in 3 levels, being low that a person is not engaged, there's no engagement or thought process being in the task. Normal, consider that the normal input or constraints that you can have as performing a task, and high being that you're completely overloaded. We try to understand the cognitive load as we were doing some experiments, including something called dual tasking. Hence, there was a task at hand, which was driving in our case, and we had to introduce a different task altogether at the same time as you were driving, in trying to raise this cognitive load, understand how this works, considering that very high or very low cognitive loads would decrease performance. With very high, I mean that I'm doing 2 or 3 tasks at hand, hence I cannot do them all together. And low cognitive load means that I'm really not doing anything at all. I'm just cruising, driving, or just waiting for the task to be over. And understanding this process is also something that is crucial, at least for HRI in our perspective. Again, what is the application, at least in the context that we were given for glovebox teleoperation for HRI in general. Doing for teleoperation some performance analysis for training, it's useful if we consider task modeling and cognitive load modeling as the inputs of that. We can see that the training has been done successfully, that people are engaged, and that the movements and the tasks are being performed as we designed them. Also, cognitive tracking for optimal performance, as you need to have the optimal normal cognitive load. If you are overloaded or underloaded, it means you won't be able to perform the best you could. And also, as Ozan said, closed loop aided control, hence try to for the robot to be a little bit more clever of what we're asking from him, but understanding when the human needs some help or not, because this type of negotiations from a haptic perspective are also an interesting topic. And for human and robot interaction, again, more open-ended cooperative tasks, designing interfaces and validation. What I mean by that is that an open-ended interface as a virtual reality interface can have some restrictions in the long run, as well as some type of joystick or specialized designed interfaces. And understanding cognitive load, understanding movement and the task at hand can help us better design this, better validate it, and have a long, useful life as we are operating. I hope I wasn't too quick. I think it was just about time. And thank you very much. If you have any questions, I'm happy to answer them through the chat.
That's great, thank you. while we're waiting for people to type any questions for Erwin, just going to go back to the question that was in the chat for Emily, because I believe it'll be easier for her to answer it verbally rather than typing. So I'll just read it out. The question was, was from Emily's talk. Is the default in the situations you described to use live, real-time control via joystick, etc., or can the entire input from H to R be slowed to commands that are input, considered, and then sent or released to the robot separately once checks have been completed in human team discussion on that command? It seems that slowing H's input time effectively increases H's reaction speed. This would still require very smooth and reliable movements from R, but just in smaller movement pieces. This would mean R waiting mid-movement a lot, but might mitigate against human fatigue, etc. So, Emily, do you want to answer that now?
Sure. So, specifically then, the maintenance of the small jet fusion reactor, an experimental reactor in Oxfordshire, is done with a one-to-one kinematic robot master-slave device called Mascot. And Mascot is able to be paused, or you can put the brake on it in order to figure out what your next steps might be, given the maintenance task that you're undergoing. And in the design and production of that system, a lot of cues were put in place. For example, more visual cues in front of the operators themselves, so they knew whether or not those brakes were in at all places along the system, to avoid things like thinking everything was stopped, but it wasn't, and drops occurring within the vessel. So in a roundabout way, what I say is, in that specific situation, what you describe here is possible and does occur, and it does indeed mitigate against things like humans having to hold things in place whilst they decide what the next step should be. But in the training and development for that particular system, a whole bunch of different questions and key issues arose that then needed to be dealt with to make sure that the movement was smooth and reliable, because of things as simple as letting go of brakes without knowing they were on. But specifically, not specifically, of fundamental importance here is that is one situation. And as you increase layers of autonomy into your human-robot system, what you would really like to see, because of the massive complexities of larger structures that would need to be dealt with, is the ability for the robot to conduct its reliable movements without having to be stopped and started so much as the humans make decisions. So yes, what you say, Simon, is right, but you still need to take into consideration what the robot's actually doing and where it's doing it.
Great, thanks, Emily. Someone just asked about the presentations being available, the recording being available afterwards. Yes, if you just contact the Rain Hub, we'll be able to send you the link. And then we've got a question, I presume this is for Erwin. It's, can the learning with one use to be extrapolated to a different user from the dimension of the arms? I hope I've read that properly, Joaquin. Does that make sense? Erwin?
Yes. Hello. Joaquin, thank you. I say yes. What happens is that, at least for our experiments, we use different type of people with different arm lengths, with different postures, and different movements. And we did manage to do this. However, we had some caveats. For instance, you cannot use arm length, for instance, or arm position as itself, because it is really different. So you need some type of normalization of this type of information. Sorry, I think you don't see my laser pointer. You need to have some type of normalization of these inputs. That's one step. Second is that as people are different, even for arm lengths, and if you can consider the dimension, the arms dimensions as trivialized, and you just normalize it and that's it, the movements itself are different. Hence, if I make a model just specifically for Joaquin, it's not going to work for somebody else perfectly. What I mean by that is that for going straight, the angles in your elbows can be different as you do the model. So you need more data of people that have different patterns, driving patterns, and driving styles, which makes it better. So you cannot do it with one person alone because it's very challenging. If you have enough people, at least with our models, it can be done. So you don't need 100 people, but just enough that the model can understand several type of movements. So I would say yes, you can do them, but it's not straightforward. It has this process of knowing more about who is driving and what type of movement are you doing. I hope that answers your question. Yeah, thank you.
Right, that's great. I do apologise. We've gone over time a little bit here, so I might
Sorry.
not, no, I might not be allowed to host again. But just to say thank you for all the presentations today. It's really interesting. Just a reminder again that we don't have a session next week, but we're back on the 11th of June, where we've got a legged robot special. We got talks on the Animal from Oxford and 2 really different styles of hexapods, the Corin at Manchester and the Nottingham hexapod. So hopefully you'll be able to make it then. I'll stay online a few minutes longer just in case anyone has any other questions, which I can then pass on and can get back in touch with you with any answers. So thank you. I hope it's the sun's shining where you are. So enjoy the rest of your day. Okay, bye.